So today I would like to share with you some of the work that we have been working on, particularly on localization and coordination of mobile robots in strong geophysical flows. So geophysical flows such as hurricanes and ocean currents, they are quite common and very important phenomena. So for example, what's showing here on the background is the large-scale surface current inside Pacific Ocean and a little bit of the Gulf of Mexico. So being able to understand these flows and predict their dynamics are very, very good, important to global weather forecasting and even coastal economy. So far, remote sensing is still the primary approach to collect data about this phenomena. So there are some sort of in situ observations are being made by mobile sensors, but many of them are passive sensors. So it is highly desirable to have mobile robots to go into these strong background flow environments and make in situ measurements so that we can have more informed modeling and prediction about this flow phenomena. So recently, platforms like small scale UAV systems or autonomous underwater vehicles are getting much smaller but even smarter thanks to the battery technology and microprocessor technologies. So most of my study is focusing on how can we enhance the autonomy level of these small scale mobile robots so that they can navigate, sense, and learn these geophysical flows much better. So although these robots are getting smarter, but they are facing a unique challenge that ground vehicles that they typically just don't share, right? So as the robot becomes smaller and their mobility is highly limited by the background flow dynamics. So to put things in perspective, basically, so if we look at a typical speed of a robot versus the background flow fields for aerial vehicle, so they typically are around 15 meters per second for fixed wing aircrafts. But if we look at typical hurricane speed, they can be as large as 75 meters per second. So there's this huge difference in terms of the mobility of the robot and versus the background flow. So it is simply impossible for this vehicle to just directly fly against the hurricane. So it is a little bit better for underwater vehicle, comparing against a background ocean current, for example, typically as large as 3 meters per second, and versus the vehicle's typical speed of 2.5 meters per second. But still, we are dealing with a situation where the maximum actuation capability is on par of the background flow dynamics. The second challenge faced by these small robots in flow environment is disaggregated navigation. So typically these environments are GPS denied environment, so which makes their navigation and localization super challenging. So to deal with GPS denied localization, self-driving car often utilize relative measurement with respect to the vehicle itself and some surrounding features to construct a local map to better guide their navigation. But this is simply impossible for a UAV system flying within the hurricane eye wall, for example, or an underwater vehicle navigating in the middle of the ocean, because there's just no such features for the vehicles to leverage. And lastly, I would like to mention that many of the sensors have very limited perception range. So if we assume that we are using a single vehicle to sample the entire ocean, for example, so this is the Hugin AUV, and this vehicle is depth rated at 6,000 meters. And if we assume that we're using this vehicle, and assuming that this vehicle can sample 1,000 cubic meter per second, which is already pushing it, and it will take this vehicle about 42 million years to sample the entire ocean, which is simply impossible. So to this end, many times we leverage a swarm network of mobile sensors to sample the large scale background flow field. So the Argo project, for example, so far has deployed about 4,000 floats. And these floats are designed to have the capability to change their depth and park at a particular depth and drift with the background flow while they take the sensor samples. Although it seems it's still a little bit inefficient, but the Argo project is arguably one of the most exciting breakthroughs for marine sensing in the past decades. So conventional design thinkings for aerial and underwater vehicles consider background flows are either adversarial or negligible disturbances that the vehicle has to either compensate for or have to avoid at all cost. So I believe that the reason that we're thinking it this way is because we lack understanding about the fundamental fluid dynamics of the background flow. So if we have information about this background flow, I would like to show that this information can be used so that the background flow can be considered as transportation highways that help improve the mobility of these sensors, or to be used as ubiquitous navigation reference that helps the localization of these robots, or as inspiration for us to better design multi-robot systems to help us better model and control swarm of robots. So our work has been primarily focusing on all three frontiers that I mentioned here, but due to the time limit today, I'm going to primarily focusing on the second and the third one. So I should mention that although many of our proposed solutions are also applicable for aerial systems, so I will be focusing on autonomous underwater vehicles for the rest of the talk. So in the first part of my talk, I would like to briefly share some of the work that we've done on flow-aided navigation. So the second part is about flow inspiration and how we use this as a way to model and control. How we use flow inspiration to model and control a swarm of mobile robots. And very briefly, at the very end of the talk, I want to share some of the work that we have been working on to potentially establish a marine robotics testbed in Hawaii. So I know that this is a virtual presentation, so I try to get to these parts by this set time marker. So if you have to step away, feel free to do that. So first off, let's talk about flow-aided navigation. So for mobile robots, the capability to accurately localize themselves is one of the most important prerequisites for them, because it is very important for the robots to know where they are so that they can make very adaptive motion decisions on the fly. Also, it is important to know where they are to enable them to follow a trajectory that are designed by the user, or to simply georeference the sensing results that are collected by these robots. So underwater localization is inherently challenging because the seawater is opaque to radio frequency signals. This means that GPS signal simply doesn't work underwater, and RF communication is largely unavailable for underwater robots as well. So before we get to flow-aided navigation, I want to give you a 3-minute crash course on localization. So oftentimes the word localization is interchangeable with navigation, so I'll use them interchangeably here. So what I mean by localization is to really assign or keep within some sort of definite locality. So this definite locality is often defined with respect to some known features. So this feature could be satellites of the GPS system or some sort of established maps ahead of time. So if we look at all of these existing localization methods, we can simply classify them into 3 categories. The goal is always to find out a best estimation of my state x of k. And for example, in the 2-dimensional navigational problem, so where my state vector can be defined as my xy coordinates along with my heading angle phi. So this is for planar motion. So typically we have to deal with a much higher number of degrees of freedom for mobile robots. So the first type of navigational method doesn't require any reference at all. So simply the vehicle measures the velocity and the acceleration of its own motion change. So this is typically called odometry or inertial navigation system. So by measuring the velocity, for example, we can deduce the vehicle's current location based on the previous location by numerically integrate these velocity measurements. So simply, if you have an inertial measurement unit, which has accelerometer that can measure the acceleration of the vehicle, you can double integrate acceleration to get your current position. So this is a very simple but highly unreliable navigational approach. For example, so most of our smartphone nowadays have an IMU system on there already. But the drifting area is very, very large if you do not have additional correction to this drifting area. So for example, your cell phone can drift for 1 kilometer simply within 5 minutes, right? So typically this inertial navigation system are used alongside of some other navigational approach. So this leads me to discuss the second category, which is utilizing some known feature location. So here, Y of K represents the location of the feature that are known, and they can either be static features or mobile features. For example, the global navigation satellite system, we can consider the location of the satellites as the known feature here. And if we have some sort of map given ahead of time, and these features are static feature, the location of which that are known to the user. So what the vehicle does with this feature is that it measures the relative position with respect to these features so that you can triangulate or trilaterate your location of the robot. So this is probably by far the most widely used navigational approach that are drift-free. So a third type of localization strategy is a generalization of this GPS-based localization. But now we're not dealing with isolated feature anymore. Instead, we're dealing with the continuous spatially changing quantity. So you can imagine, for example, the magnetic field inside a building as your navigational feature. So what the vehicle measures is actually the field value at the location of the robot. For example, I can measure how strong this magnetic field is at my current location, or how strong my Wi-Fi signal is at my current location, right? So this strategy has been widely used for indoor navigation systems using RF signal strengths or light source strengths, for example. But one thing is I should mention is that this field is assumed to be time invariant. Okay, so if you have a time varying field, there's going to be complication. Okay, so all of these three categories of localization methods is somewhat utilized for underwater localization. Okay, so for example, if the vehicle is close enough for the water surface, the vehicle can resurface every now and then to correct their inertial navigation error. Alternatively, if the vehicle can stay close to some sort of navigational beacon installed on the sea surface or on the sea floor, the vehicle can correct their drifting error of their navigational system as well. Or if the vehicle is further close to the sea floor, you can use simultaneous localization mapping, which allows the vehicle to construct a map of the seafloor and localize itself with respect to the map. But if you look at this figure, all of these existing strategy limits the vehicle to either the close proximity of the sea level or the seafloor. So there's a large middle depth range here that the vehicle can only utilize inertial navigation and suffer from a long-term drifting error. And there's no feature to help the vehicle to correct this error. But if we think about it, so we do have ocean currents everywhere. And we actually know some information about the ocean current. We have been using ocean circulation models to simulate and predict the dynamics of these ocean currents. And right now, we are able to actually predict this ocean current up to a week with a temporal resolution under 1 hour and spatial resolution somewhere on the order of hundreds of meters. So if we give this sort of information to the vehicle, can we help the vehicle to navigate better? So that is the first question I would like to address here. So this new type of localization method, which we call a flow-aided navigation, is exactly using the background flow information to help the vehicle to improve their navigational accuracy in long-term mid-depth navigation missions. So here, the reference is simply background flow fields, which is spatial temporally changing. So if we were given this information, so the robot is able to measure its relative velocity with respect to the background flow at any given location, right? So with this relative velocity observation, I can deduce the vehicle's location. And this is how I perform localization using flow field information. So on the very high level, flow-aided navigation utilizes two different sensors that are commonly found on long-range underwater vehicles. The first one is called Inertial Navigation System, or INS, which measures the state change of the vehicle itself, which includes the angular velocity and the acceleration of the vehicle. The second sensor, which is called Acoustic Doppler Current Profiler, or ADCP, which measures the relative flow velocity with respect to the vehicle. So what flow-aided navigation simply do is it try to construct a discrepancy between the estimated relative flow velocity, which is a function of the vehicle velocity, and the model predicted background flow velocity, and the actual flow velocity observation. So this error essentially goes into my estimator to be used as a feedback signal. And this signal will guide me to better estimate the vehicle's position at the right at a given time. So mathematically, let's look at this particular case where I have my state as a 12-state vector. So here P represents the position of the vehicle, V represents the linear velocity of the vehicle, and psi here represent the heading angle of the vehicle. And these three B terms are essentially representing my time-dependent bias signals of my sensor. And this UC term, which models, this UC term is actually modeling the difference between my model predicted background flow velocity and the actual background flow velocity, because the model prediction can only capture large-scale flow phenomena. So this UC you can consider as a small-scale background flow. So in this case, what we're trying to find out is this conditional probability density function, which is my state vector estimation x of k, given all of my sensor measurement u and z and my initial position. So what u and z represents is that u encodes my state change from time k minus 1 to time k. So this can be obtained by my inertial navigation system. The second quantity, zk, is essentially my relative flow velocity. So if I know my current velocity of the vehicle, and I was given the background flow forecast map, I can deduce which is the theoretical flow velocity here. So I can essentially estimate what should be my relative flow velocity, and I can use that to compare against the actual observation. So simply, I'm trying to look for this probability density function. So another way to think about this is that we're trying to find out the best set of value for my xk so that I can explain all of my sensor measurement most accurately. So this estimation problem can be essentially solved using Bayesian analysis. So I can find out this Bayesian recursion, which depends on my vehicle model, my previous time step estimation, and my flow observation model. So I can update my position estimate recursively. So similar to many other Bayesian estimation problems, this integration cannot be calculated analytically. So we have to rely to some approximation schemes. So we have to make some assumptions here so that we can solve this approximation problem. So there are two types of approximations that we can make. The first one is we can use a parametric estimator, which means that we can assume that there's some certain quantities that these variables, we can assume that these variables follows a certain distribution that can be parameterized by a certain function, right? So for example, we can assume that this velocity signal follows a Gaussian distribution, right? The benefit of using parametric estimator is that they are computationally efficient because we have analytical expression for these distributions. But the drawback of them is that they are often struggled at representing very complex distribution, especially for when the distribution has multiple hypotheses. If you want to track multiple hypotheses at the same time, it's difficult to use a parametric estimator. So if we look at flow-aided navigation, so we are actually dealing with the highly ambiguous feed map, location maps here. So this is the background flow map, or it's simply a vector map. So if you were given a particular background flow velocity vector, you can find multiple different locations where we can find the same exact background flow, right? So this suggests that we might want to use a non-parametric estimator to estimate the position of the vehicle. So this is a particle representation of a multi-model Gaussian distribution using a non-parametric estimation scheme. So basically what we came up with is that we want to sample the location P here. Then after we get a sample distribution of the sample estimate of the location of the vehicle, we can marginalize away this particular variable, and then we can estimate the rest of this vector using a parametric estimator, which is much more efficient. So here we are designing essentially a bank of extended Kalman filter here. So we first perform important sampling on the location of that, on the position, on the location of the vehicle here. So for each copy of this particle, so it is essentially performing extended Kalman filtering. So we have n copies of extended Kalman filter. For each of these particles, we also assign some sort of weight that is representing how likely the result of each of these particle, each of these EKFs are. Then the particle filter essentially select the best particle and also redistribute the weight based on how likely.
All right, sorry for those technical difficulties, but we're back.
Yeah, hopefully this will last longer this time. So basically, I'm trying to avoid showing the previous slide to avoid this issue. So what we found out is actually the flow-aided navigation strategy is a consistent and also unbiased estimator. So we also find an interesting thing that if your background flow has larger variation, your localization variance is actually smaller. So this is quite straightforward because we're using the variation of the background flow as a source of information to guide us to do localization. So in the limit, when the background flow becomes a uniform flow field, the flow-aided navigation strategy actually degenerates to essentially bottom locking if the vehicle is navigating with respect to the seafloor. So we can obtain direct velocity correction to the vehicle's velocity. So here we are comparing the flow-aided navigation result against the only alternative that is available out there, which is water tracking here by Manoa here in 2016. So here, what we do here is we establish a simulation scenario where we are using actual field test data. So this is a data set where a surface vessel samples the Gulf of Mexico and Gulf Stream back in 2012. So we take the trajectory of this surface vessel. We also take the ADCP measurement carried by the vehicle here. So we are focusing on this small area here, where this trajectory lasts for about 25 hours. And we apply this flow-aided navigation method on this trajectory. And we find out that we can actually obtain a localization accuracy that is comparable or even better than the single alternative out there. But one thing that I want to mention is that we allow the similar performance by using a navigational sensor that is 2 to 3 orders of magnitude cheaper than the alternative approach. And we also allow a much longer navigational duration. So here we're comparing 25 hours versus 1.5 hours and 6 hours to 5 minutes here. So the reason that why the localization error increases is because we don't have absolute reference here. Although we have model forecast of the background flow velocity field, but this model forecast has a very large error inherent. And secondly, this forecast accuracy will degenerate quickly if your forecast lead time increases. So for example, here we can compare the ADCP measured flow velocity against the ocean general circulation model prediction. So you can see this large gap here. So we are actually trying to bridge this gap by using the UC term as you saw previously in the state vector. But still, so we are depending on the accuracy of the ocean flow forecast model here. So that makes us think that can we free this flow velocity estimation of, can we free this flow aided navigation strategy from the dependency on these ocean circulation models? And essentially what we're looking for here is some strategy to construct a flow map on the fly, then use this flow map to localize ourselves. So this is very similar to simultaneous localization and mapping for ground robots. Simultaneous localization, or SLAM, is essentially trying to come up with a map of unknown environment and localize the vehicle within it. So on the very high level, what it's looking for is actually the location of the robot and also the location of a bunch of features that are static, given the measurement of how the vehicle changes its position and what are the relative measurement between the feature and the robot itself. So SLAM has been a very, very important building block for a lot of cutting edge technologies, such as the self-driving cars and augmented reality here. So one premise is for SLAM is that all the features are static. So if any of the features are moving, we simply cannot get a converging estimation, okay? So this becomes an issue if we want to go from conventional SLAM for what we call fluid SLAM. Right now, we are dealing with a dynamic fluid environment. So this is a flow map here, phi of x of t. So we also want to estimate the position and the velocity of the vehicle. So this is a very ill-posed problem. I don't know how to solve that, but we can simplify this one by assuming that my flow velocity field is time invariant. So this becomes a solvable problem, although that we are trying to estimate both the location and the velocity of the vehicle. And actually there is some codependency between these two quantities. You can derive the other one if you know one of them. So if we further reduce or simplify this problem by assuming that we know the velocity of the vehicle, so this reduces to localization given some field quantity. So this is something that people have solved before. For example, if you have a Wi-Fi signal field, which is phi of x, you can localize the location of the robot by measuring the signal strength of your vehicle. So actually, some of the high-end Roomba robot vacuums are able to construct a map of your Wi-Fi signal strengths at your place and also localize itself within it. So if we look at this time invariant fluid SLAM problem, and if we use some sort of finite representation of the flow environment, here we are using a grid mesh to represent the flow field. Now we are reducing this high dimensional flow field to a very low dimensional vector field. So which is, we're trying to deduce the position of the robot, the velocity of the robot, and also my flow velocity vector at the grid node's location, and given all of these sensor measurements. So this becomes a maximization problem to maximize my my posterior distribution here. And this can be transformed into a minimization problem that minimizes the error associated with my sensor measurement and my state, my model prediction. So here I'm trying to find the best set of state variable essentially, so that I can minimize this error, this J fluid SLAM cost function here. So by applying the fluid SLAM to this very simple single gyro flow field, so we can see that the vehicle can faithfully reconstruct its trajectory and also estimate the background flow velocity fairly accurately. Okay. So another way to look at this is that if we were given a time invariant flow field, we are able to conduct fluid SLAM. But there are a bunch of things that we would like to address in the future. First of all, we would like to look for alternative representation so that we don't have to use a mesh grid represent the flow field. So some mesh-free flow representation will be desirable. For example, Gaussian process is something that we're looking into right now to replace this mesh grid representation. Then fluid SLAM becomes a real-time Gaussian regression problem. We still have unknown variables, which is the training location of the data. So here we are also looking into how can we come up with reduced flow representation model. For example, if you have some preliminary data about the background flow field, can we obtain some of the POD modes and use this as a reduced representation of the flow field? So in the future, we also would like to look into time varying flow fields and also real-time SLAM, because so far we are looking at the problem of batch processing, where we analyze all of the sensor data altogether as opposed to on the fly. So this becomes a super challenging problem because we do not have a global information about the flow field. So before finishing talking this section, I will also want to mention that even if you can perform fluid SLAM, you don't want to throw away the large amount of information general circulation model are providing you. So this is a scenario where we can use general circulation model to predict large scale dynamics. And then you can use fluid SLAM to establish a subgrid model. And if you merge them two, what you end up with is a half fidelity ocean model. And this model can also provide you what are my error residue of my flow estimation. And you can construct an uncertainty map, which can guide my future path planning for the vehicle to gather more data. So you can almost think this as I'm trying to find out the hot spots where the vehicle will provide me the most informative measurement. So the next part, I'm going to talk about a very different topic, which is flow-inspired multi-robot coordination. So swarm robotics is quite important because they allow a very robust performance, so that the vehicle, the sensor measurement network is robust over individual agent failure, so which allows efficient distributed sensing and also significantly simplifies a multi-agent path planning problem. So many of the swarm modeling and control approach are inspired by these emergent dynamics we observe in nature. And so to model a swarm so that they demonstrate these emergent dynamics, it has been found that there are two key characteristics that we have generated. The first one is separation, meaning that the agent has to be separated away from each other so that they don't collide with each other. The second one is called cohesion, means that the agent has to stay close to each other so that they are not separated from the rest of the swarm. In order to have a flocking behavior, which as we observed in fish schools and bird flocks, we also want the agent to have the capability to align their moving directions. So all three characteristics here are very, very important in guiding the swarm control approach here. So to design a very good swarm strategy, so there are two issues need to be addressed. So first one is, what are my inter-agent interactions? What is my law that governs my inter-agent interaction? The second one is, what is my emergent dynamics? Can I describe the dynamics of the large swarm? So the first type of swarm control law basically applies a bottom-up principle. So what that means is that I explicitly define my inter-agent interaction law. So this is good in the sense that if I want to apply this as a distributed local interaction, so that I can scale this up to a very large swarm. But the drawback of this approach is that it's very, very difficult to obtain emergent dynamics of the swarm. We have to amend to Monk-Howard simulations to have some statistical sense of the performance of the emergent dynamics. So another approach is what we call the top-down approach. Here we first prescribe the emergent dynamics of a large swarm. Then we try to derive what is my local interaction law to give me these emergent dynamics. So we are essentially focusing on a top-down scheme here. The reason that we want to model swarms as fluids is because fluid particles, they meet all of these requirements that we look forward to from a very well-behaving swarm dynamics. First of all, the conservation mass in fluids enforce that the fluid particles cannot occupy the same space at the same time, which allows us to perform separation among these agents. And secondly, the intermolecular attractions, the pressure inside the fluid medium, and the body force gives us very cohesion phenomena in fluid-like swarms. And lastly, the viscosity effect gives us very good velocity alignment, as you can see later. Most importantly, since we are modeling the swarm as fluids, we have a governing equation that can be used to describe the general dynamics of this swarm. Okay, so to do so, we have developed a series of swarm modeling and controlling approach based on smooth particle hydrodynamics, or SPH. SPH is a mesh-free computational method widely used in simulating fluid flows, and it was initially designed back in the 1977. Some of you might know that SPH has been used in a lot of visualization of special effects in movies. For example, in the Lord of the Ring, so the scene where Gollum is falling into the Mountain Doom trying to catch the ring, the lava is essentially simulated by using SPH. So what SPH does is that I take the conservation laws of fluid mechanics. I apply a kernel approximation so that I can decentralize the calculation of my fluid dynamics into a small number of particles here. So here I can derive my SPH governing equation, which governs the change of my density, my pressure, and also my velocity here. So by using this SPH governing equation, I can derive my local interaction law to control a swarm by simply defining a particular viscosity model and also adding some damping term to preserve stability of my swarm. So this is my flow-inspired swarm control law, essentially. So by controlling a swarm as fluids, obstacle avoidance and flock guidance becomes very, very simplified. So for obstacle avoidance, I can simply just introduce a high density particle, which will allow me to create a high pressure region. And this region will repel the vehicles or the agent away from this region. For flock guidance, I can introduce a very low density particle, which will create a low pressure region and therefore attract these particles towards this region. So for example, this simulation shows that two heterogeneous swarms are heading towards their different target while they are avoiding the obstacles here. So here obstacles, I'm assigning high pressure, high density particles. And for target here, I'm assigning a low density particle to attract these swarms towards them. So I can simply use swarm as a path planning high level controller. And then I can then assign these SPH trajectories to a low level vehicle controller to handle the physical constraints of the platform in practice here. So here I'm showing that a swarm of 15 fixed wing aircrafts are trying to follow a dynamic target. So here the trajectory of these airplanes are generated by the SPH swarm control law, and the local stability control and the trajectory following are controlled by their vehicle controllers. And similarly, I can also assign hotspots in the area where there are obstacles, and different heterogeneous swarms can apply the same SPH control law to avoid inter-agent collision and also converge to loiter circle around the hotspot locations. Most importantly, I can use this SPH to simplify my optimal path planning problem in a strong background flow field. So for example, if I want to guide a large number of agents from one location to another where there's strong background flow going on in the background, so conventionally, I will have to design a very large number of optimal trajectories so that these trajectories are minimizing their individual energy cost, but also avoiding collision among these agents. So we know that this is an NP-hard problem for multi-agent path planning. But if we're controlling this swarm as an SPH swarm, we can simply just compute one single energy optimal trajectory, then assign this trajectory to the virtual attractor and allows the swarm to follow this virtual attractor. So it's shown that as long as the flow variation within the radius of the swarm is small enough, so each of the agent energy cost for each of the agent energy cost is nearly optimal here. So we can also show that the on average per agent energy cost scales according to this the equation here, which is a function of the radius of the swarm and also the optimal energy cost for this single trajectory. So we can also show that the SPH swarm control law is asymptotically stable by using the Lee-Opton stability analysis. And most importantly, we can apply many of the fluid dynamics strategy. For example, here, if we perform a non-dimensionalization analysis of the SPH swarm control strategy, we can find out that the inter-agent control law is actually a combination of two terms. The first term governs the level of cohesion that we obtain from the swarm. The second term governs the degree of velocity alignment. So actually these two terms are weighted by the ratio between the Mach number and the Reynolds number, which is super powerful in guiding us to design a very large swarm's emergent dynamics of a large swarm. So about extending this work to future directions, there are two directions I want to mention briefly here. So first is swarm flow interaction. So here's a simple example where we're trying to preserve the connectivity of the swarm in the strong background flow fields. Here we're looking at is meandering jet flow field, and the color here shows the Lagrangian coherent structure that represents the separation of different fluid regimes here. So as you can see, if I release 50 particles here that are controlled by a simple swarming control law that maintains the particle not being separated by the background flow, and it actually goes into this fast transportation channel here in the middle of the jet. So this indicates that there is a strong coupling between the swarm dynamics and the background flow dynamics here. So this means that in order to define a swarm connectivity preservation law, we not only have to look at the swarm dynamics, but also need to pay attention to the background flow dynamics. So for example, here, if we analyze FTELE field, which quantifies the local stretching of the background flow, this is a double gyro flow field. And we can see that we have high stretching in these areas. If we assume that we are quantifying the stretching among particles that are actively controlled by this local interaction law, we can see a different stretching map. And this stretching tells us at what location we need to apply local actuation so that the agent will stay together. So this design philosophy is guiding many of our work recently to design much intelligent and smarter swarming strategies here. And very briefly, this another direction that we're looking into is how can we co-design formation control and localization together so that we can encode resilience into multi-agent systems here. So here we're designing a controller that is aware of what localization strategy the vehicle is currently using here. So we are designing a redundant localization system that can use either GPS or relative localization or inertial navigation to find out the states. And so we are assuming that the GPS is prone to be under attack, and that the controller is aware of when the GPS is subject to attack and try to fall back onto relative localization or initial navigation whenever necessary. So on the right-hand side here, as you can see, that's the resilience version of formation tracking. And the GPS attack starts at this particular time step. As you can see, two different cases are performing equally well before the attack. And once the attack happens, and now the formation is changing it to a triangle. And the resilience version is performing much, much better than a non-resilient control strategy. So by applying this co-design philosophy, we would like to design much more resilient multi-agent system that can sustain GPS attack or any other communication attacks. So to close out this talk, I want to very briefly plug in some advertisement of the marine robotics testbed that we're trying to establish in Hawaii. So some of you might know that near the shore of Honolulu, we have a study area called Kilunalu, which is a shallow water reef observatory site, and where we have cable power and communication are maintaining a bunch of sensor nodes on the seafloor at the depth of roughly 10 to 20 meters. So what we are trying to focus on is try to deploy multiple underwater docking stations and multiple resident autonomous underwater vehicles to allow a remote user to deploy their algorithm onto these vehicles without having to be present on site, then test out their autonomy algorithms. The purpose here is to really accelerate marine robotics research and education, and also include as many people as possible in this. So for this, we're teaming up with the Hawaiian Spaceflight Lab, where they have developed a series of softwares that has been applied on multiple satellite missions. And we are transferring their software suite for a marine application here. So we look forward to execute the first remote user request by the end of 2021. So stay tuned for that. So with that, I would like to acknowledge my current sponsors, which is University of Hawaii and the Department of Energy, and also some of the agencies that sponsor my PhD study at University of Florida. I would also like to thank my collaborators, Cameron Mosini, Dr. Pinsky, and Matt Silic, and Yin-Chen Liu for the collaboration on the material that I talked about today. And especially I would like to thank Steve and the Department of Mechanical Engineering for hosting me last summer. And I'm happy to take any of your questions. So do we have any questions in the chat box?
So I have a question. I don't want to take away from anyone else who wants to ask one first. Yeah, maybe I will ask mine. So Juyon, I know you've talked to me before about some of your efforts in understanding kind of navigation systems of some of the indigenous Pacific Islanders to get from island to island. And that's such an interesting topic. Would you mind just telling us a little bit more about that?
Yeah, so that's actually a very, very interesting strategy, because we found out that the Pacific Islanders and the ancient voyagers, they are essentially trying to read the wave patterns and the flow patterns to find out where the islands might be. So this is very similar to trying to construct a map of the flow field. But they are reducing this flow field mapping problem to a low dimensional problem where the representation becomes the location of the islands. So you can simply imagine that if you want to create a background flow field using multiple cylinders in the flow field, right? So we are trying to reconstruct the location of these cylinders and to inform the navigation of the robot. So that is something that we are trying to use as inspiration in our design for fluid navigation here.
Very cool. Thank you.
Yep.
I have a question.
Yep.
So regarding the swarm robotics control, are they fully decentralized? It seems like modeling the swarm control from like top down approach put the system as like a centralized, meaning that each agent has an access to the desired goal. So Yeah, are they fully decentralized or centralized?
Yeah, so the one of the nice thing about SPH control strategy is that it's fully decentralized because it's using this kernel function to approximate these continuous quantities. So you can enforce a compacted bounded kernel, so which has a limited boundary. So which means that agents are beyond the radius of the kernel are not being considered when you calculate your local interaction loss. So this is a fully decentralized scheme.
Okay, thank you.
I have a question about the kernel size. Is it adjustable to fit so that there's always at least one swarm robot within, I guess, within the radius of the kernel, or is it like self-adjustable, or do you pick that and it's stuck that way, or how do you pick the size?
So yeah, that's a very good question actually, because typically we choose the kernel ahead of time, but you can definitely make it adjustable. So typically the way we choose them is based on how far the agent can sense each other or can communicate each other, right? So you can definitely define anisotropic kernels so that it fits to your particular communication pattern, for example. So this is actually quite common for SPH simulation for fluids. For example, if you want to simulate the surface of a fluid medium, so there the kernel for the particles on the surface will be very different from the kernel that is within the fluid volume. So yes, it is totally adjustable, and you can define adaptive kernel length if you want.
There was a question in the chat from Brian Pelagi. If Brian, you want to unmute yourself as you're pretending to be Michelle, or tandemly watching the seminar.
They're trying to preserve bandwidth. That was a really nice talk. I had a question about the robotics testbed at Kilunalu, where
Yep.
I believe you'll be more influenced by waves than currents. Do I have that correct?
Yes, that's correct.
So in terms of thinking about vehicle control under the influence of waves, obviously different timescales, different forcings, especially in an irregular directional wave field. Have you given any thought to how this might be expanded to incorporate that aspect of ocean forcing?
Yeah, that's exactly why we want to use Kilunalu, because there's a lot of wave breaking and there's a lot of background flow variations. And currently there are a couple of ADCPs, I believe 3 to 4 ADCPs mounted on C4 that gives us the ground truth of the background flow velocity field. And we want to use that as a way to test our vehicle navigation strategy using the background flow field. Because as I mentioned, we want to have a very large background flow variation to be able to localize. And regarding the vehicle control, so one of the collaborators that we're working with, so he actually is designing a bunch of vehicle control strategies that are using these fish lidar line inspired sensors to be installed on these vehicles. The vehicle can essentially measure the flow, the incoming flow, before the flow impact the vehicle to create a control error. So you can use a feed forward control strategy to compensate for this wave. So these are something that we also want to test out with this marine robotics test bed here. So that is a very interesting research question, actually.
Thank you.